Hello. So we have now learned everything we need to know about crystal structure in 3D. We learned about all the lattices we want to discuss. We learned about lattices and bases. But at the end of the day, what we really want is to describe physical phenomena in these crystals. And more often than not, what we are interested in is waves of some sort, whether vibrational waves or phonos, whether they are electron waves, electromagnetic waves. And the world of waves is actually the world of reciprocal space. Okay, so today we will start with the chapter 2, where we will be talking about X-ray diffraction, and that's where we will be discussing about waves and reflection, refraction, and whatever is happening in this area of X-ray diffraction. And we will also be discussing reciprocal lattices, okay, or reciprocal space. So let me start with reciprocal space. Every lattice, so what we learned so far is what we will be calling from now on direct lattice. Okay, so a direct lattice is a lattice that has primitive lattice vectors A1, A2, and A3, where we can reach any point in the lattice by vector R, which is an integer number time multiplied by these primitive lattice vectors. So from now on, this space, we will be calling it direct space, okay? Now, for each direct space, there is a reciprocal space. There is a reciprocal space where it also has its own primitive lattice vectors. And to differentiate them from A1, A2, A3, we will call them B1, B2, and B3 in such a way that we will have this vector G is equal to V1 times B1 plus V2, B2 plus V3, B3, where B1 is 2 pi A2 cross A3 over A1 dot A2 cross A3, B2 is 2 pi A3 cross A1, A1 dot A2 cross A3, B3 equal 2 pi A1 cross A2, A1 dot A2 cross A3. So all you have to remember from all this is that for every direct lattice, there is a reciprocal lattice where for every A1, A2, and A3 primitive lattice vectors, there are B1, B2, B3 that I can derive them from A1, A2, A3, and we will see that in a moment. So we will be doing exercises where you will see how I can, if I have A1, A2, A3, I can derive B1, B2, and B3. Now, if these are B1, B2, and B3, one can easily prove that Bi dot Aj, that is, for example, B1 dot A1, B1 dot A2, B1 dot A3, B2 dot A1, B2 dot A2, B2 dot A3, B3 dot A1, B3 dot A2, B3 dot A3, it's equal to 2 pi delta Ij. So for example, B1.A1 will be 2 pi delta 1, 1. B1.A3 will be 2 pi delta 1, 3, where this delta function is a very easy function. It's 1 if I equal to j. So delta 1, 1 is 1. Delta 1, 2, 2 is 1. Delta 3, 3 is 1. Okay? And it's 0 otherwise. So delta 1, 3 is 0. Delta 1, 2 is 0. Okay? In other words, B1.A1 is 2 pi. B1.A2 is 0. We can prove it very easily by taking B1.A1 and B1.A2. So here I've written what are the vectors B1, B2, and B3. So we start with B1.A1, but I'm saying that, so what is B1.A1? So it is this thing, which is 2 pi A2 cross A3 divided by A1.A2 cross A3, and I dot product it with A1. Now look at the numerator and the denominator. This is A2 cross A3 dot A1. This is A1 dot A2 cross A3. So it's exactly the same thing. So this thing over here is 1. So what I'm left with is 2 pi times 1. So B1 dot A1 is indeed 2 pi. Okay. Let's take, for example, B1.A2. B1 is 2 pi A2 cross A3 divided by A1 dot A2 cross A3, okay? And now I want to dot it with A2. Here I just have to remember that A2 cross A3 is a vector perpendicular to A2 and perpendicular to A3. And now if I take the dot product between a vector which is perpendicular, so A2, it's whatever I have here is perpendicular to A2. So if I take the dot product, it will give me 0. Here you can just quickly remember that the dot product of any two vectors. So let me take V1 dot V2. This is equal to V1 V2 times cosine the angle between them, right? So if the angle between them is 90, and that's what I'm saying, that A2 and A3 gives me a vector perpendicular to A2. So the angle between A2 and A2 cross A3 is 90. So here, if I put 90, this will give me the dot product to be 0. Okay, so indeed, BI dot AJ is equal to pi delta IJ, where if I equal to J, I get 1. And if I different than J, I get 2 pi, sorry. And if I equal to J, I get 0. Okay. I'm gonna now turn into math, and we will do some math together. So as these ideas stick in your mind. I will not do all 3 of them. I will be doing 2 of them, or maybe 1, let's see. So find the reciprocal lattice to simple cubic lattice. Okay, so find the reciprocal lattice for simple cubic lattice. Here, I just have to remember that the lattice vectors, primitive lattice vectors in a simple cubic, I have A1 vector equal to A x vector, A2 is equal to AY, right? And A3 is equal to AZ. Okay, where these are the vectors in the direction of X, in the direction of Y, in the direction of Z, and this is vector A1. And now I want to get the reciprocal lattice. Here I'm helping you. I'm putting what are the formulas. So B1 is 2 pi A2 cross A3 divided by, I have to start by calculating A1 dot A2 cross A3. Okay, so for this, we start by calculating A2 cross A3. Let's see how easy for me it is to do this here. So here you have to remember, you do this. So this is equal to, you do this thing. Okay, here you put vector A11. So this is A, this is A, this is A. Okay. Dot A2 cross A3. Okay, let's do this again more carefully. So A1, vector A1 is AX. So here there is A, and here there is nothing, and here there is nothing. Okay, and then A2 is AY, so it is under the Y. So here there is 0, here there is A, and here there is 0. And A3 is 0, 0, A. So 0, A. Okay. And now it's a bit difficult to write in Zoom, but let's do as much as we can. And now if I do the, if I solve this, so there is A here and I multiply it. So I hide this side and this side, and I will have A squared. So I will have here A squared, A times A squared. And this gives me A cubed. Okay, A cubed. So this is a cube. Okay, so this is A1 dot A2 cross A3. So I am done with the denominator. I'm done with the denominator A1 dot A2 cross A3. Now I need A2 cross A3. So A2 cross A3 cross A3. So to do that, I repeat. So I have I X, Y, Z. So I put here X, Y, Z, okay? And for A2, it is 0, A, 0. And for A3, it's 0, 0, A. And now if I do the cross product here, I'm gonna do one of them. So as you remember how you do it. So it will be you hide. So if we're doing the X, you hide this guy and you hide this guy. Okay, and this gives me what? This gives me A square minus 0. So this gives me A square in the direction of X. Okay, then if you want the Y, you hide the Y like this, and you will get 0 minus 0. So there is nothing in the Y. And then for the Z, you hide the Z, and you will also get nothing in the Z. So the answer is A square X. Okay, so A2 cross A3 is A square X. Now, if I want to get B1, so now we will apply this B1 over here. So B1, this is equal to pi A2 cross A3, which is A square in the direction of X vector, okay, divided by, so this is divided by A cube, which is A1 dot A2 cross A3. How much is this? This gives me B1 equal to A cube in the numerator, A square in the denominator. So this gives me 2 pi. I have A square in the numerator, A cube in the denominator. This gives me 2 pi over 8. So this is B1 vector. Okay, here there should be in the direction of X, of course. So this is in the direction of X. I hope by now you remember how you do the dot product and cross product, because in this chapter, you're gonna be using it a lot, okay? So by this, we got B1. I leave it for you. So on your own, prove that in the solution, you can find it actually, but you can try it on your own before you look at the solution. This is 2 pi over A Y in the direction of Y, and B3 is equal to 2 pi over A in the Z direction. Okay, so you can do this on your own before you look at the solution, because in the coming slide, you can find the full solution, but I advise you to do it on your own. Okay, so again, as you see, if I have the lattice, if I have the direct lattice, it's a simple cubic, A1, A2, and A3, then I can calculate the reciprocal lattice vectors, B1, B2, and B3. And what we see over here, by the way, this is B2. This is B2 and B1. Okay, so I just corrected this to be B2 and B3. Okay, so now if we look at these new lattice vectors, so this is B1, this is B2, and this is B3, okay? What do they tell me about the lattice? Okay, if we compare, this is A1 equal AX, A2 equal AY, A3 equal AZ. This is B1 equals something X, B2 equals something Y, B3 equals something Z. Okay, so this, if it tells me anything, it tells me that the reciprocal lattice is, it tells me that the reciprocal lattice of a simple cubic lattice is also a simple cubic lattice, okay, of edge length or of side length, so of edge length equal to 2 pi over A, okay? Okay, so this is very good observation. Now let's do the body-centered cubic lattice. The calculation for me will become a bit messy, so I'm gonna just read for you the solution because it's already solved. So we'll do the body-centered, the cubic lattice together, but then the face-centered, you can do it on your own. So let's clear all drawings and move forward. Okay, so for the simple cubic, you find everything you need. Now, for the body-centered cubic, so for the body-centered cubic, from the question, I'm giving you what are the primitive lattice vectors. So you have A1, A2, and A3. Okay. The first thing is to get A1 dot A2 cross A3. So you just put whatever A1 is. So it is A over 2x, A over 2y minus A over 2z. A2 is minus A over 2x, A over 2y, A over 2z. The A3 is A2x minus A over 2y plus A over 2z. Okay, so you do the cross product here. Okay, so this is the first step. And once you do the cross product, now you can start calculating B1. B1 is 2 pi A2 cross A3 over this number over here. So A2 cross A3, you get it this way. This is the cross product. You need to remember how you do it. Make sure you know how you do it, okay? There's gonna be an assignment where you have to do this. There's gonna be a midterm where you will get a question where you have to do this. So make sure you remember very well how you do the cross product and the dot product, okay? So you do A2 cross A3, and then, so you got here the answer A squared over 2x in the direction of x plus A squared over 2 in the direction of y. So B1, which is 2 pi A2 cross A3 divided by A1 dot A2 cross A3 will be whatever you got here. Okay, you multiply it by 2 pi, or this is 2 pi over already, so it is done here. And you will get B1 equal 2 pi over A x plus y, x in the direction of x, and 2 pi over A in the direction of y. So the same thing you do for B2, and you get something very similar. The same thing you do for B3, and you also get something very similar. And if you look now at the primitive lattice vectors for the body-centered cubic, so what do you have for B1? You have something into x plus y. Look at the FCC. What do we have for the FCC? We have something into x plus y. For the A2, we have something times y plus z. For the A3, we have A over 2 times x plus z. If I compare this to the body-centered cubic, for the B1, it's something into x plus y. For the B2, it's something into y plus z. For the B3, it's something into x plus z. So the reciprocal lattice of a body-centered cubic lattice is a face-centered cubic lattice. Okay, and here is a summary of the results. I leave it for you to do the face-centered cubic lattice. I'm helping you already by giving you what are the lattice vectors, the primitive lattice vectors. So here you have. So you have the primitive. So the steps to get the reciprocal lattice, the steps to get the reciprocal lattice vectors. Okay, 1. Define the direct lattice vectors, the primitive lattice vectors. So these are reciprocal primitive lattice vectors. These are the direct primitive lattice vectors. So to get these are B1, B2, B3 in vector form. So to get them, first define the direct primitive lattice vectors, that is A1, A2, and A3. Okay, once you do that, you get A1 dot A2 cross A3. Okay, you get this because this will always be in the denominator. Step number 3, you start calculating B1 from the formula 2 pi A2 cross A3 divided by A1 dot A2 cross A3, and you do the same for B2 and you do the same for B2. Okay, you apply these 3 formulas over here. So these are all vectors. Okay, they have 3 components, not only 1 component. They are not integers. Okay. Now let's do another easy exercise as well. So here, consider a rectangular lattice formed by the lattice vector R equal N1 plus A1 plus N2 A2. So this is in 2 dimensions. Okay, so this should be easier. So this is 2-dimensional lattice formed by vectors A1, so direct primitive lattice vectors are A1 and A2. Okay. The reciprocal lattice vector is given by G equal V1 V1 plus V2 V2. Okay. Let A1 be 2A EX. So here by EX we mean, so A1, this is 2A, what we call X. Okay, so we can stick to whatever we call it. So A2 is, it's given, A2 is equal A in the direction. So EX and EY are the unit vectors of the X-axis and the Y-axis respectively. So I will stick to calling them X and Y so as you don't get confused. Okay, so we want to show that G is pi over A V1 EX plus 2 pi over A V2 EY. In other words, we need to show that vector B1 is equal to, or before we jump to the conclusion of, in other words, let's do the calculations of B1 and B2 and see if we really get this G over here. Okay, so over here we cannot do the B1, B2, B3 using the formulas A1 dot A2 cross A3 because this is here in 2 dimensions. So there is nothing, we cannot, this is here in 2 dimensions, we cannot do the 3-dimensional thing. But we can, what we can use is the very useful formula, which is BI dot AJ is equal 2 pi delta, so it is 2 pi delta IJ, okay, where delta of IJ is equal to 1 if I equal to J and 0 if I different than J. Okay, so let's say, so if this is vector A1, so what are the vectors A1 and A2? So I have vector A1 now, if I want to write it like this, so it is 2A 0, right? And vector A2 is 0A, right? So these are vectors A1 and A2. We want to calculate vector B1 and B2. So vector B1, let's say it is alpha 1, beta 1, and vector B2, let's say it's alpha 2, beta 2, where these alphas and betas are my unknowns. So I want to calculate them. So let's start by this. What is B1 dot A1? B1 dot A1 is alpha 1 times 2A plus beta 1 times 0. So it is alpha 1 times 2A. And this is equal to 1, right? Because I and J here are equal. So I got my alpha 1. I'm done with the first unknown. So it is 1 over 2A. Okay, sorry. Here, B1 dot A1, B1 dot A1, so it is alpha 1 times 2A. This is equal to pi times 1. Okay, so this is equal to pi times 1, implies alpha 1 is equal to pi over 2A, and that's pi over A. Okay, now B1 dot A2. B1 dot A2. This is equal to B1 dot A2. So it is alpha 1 times 0 plus beta 1 times A, right? So it is alpha 1 times 0 is 0 plus beta 1 times A. So this is beta 1 times A. And this is equal to 0 because here the I and J are different. So delta Ij is 0. So this is equal to 0, implies beta 1 is equal to 0. B2 dot A1, this is equal to B2 dot A1. Okay, so it is alpha 2 times 2A, alpha 2 times 2A plus beta 2 times 0, so plus 0, so it's plus nothing. And this is equal to 0, again, because this is I times I and J are different. So implies alpha 2 is equal to 0. And finally, beta 2 dot A2, this is equal to beta 2 dot A2, it is alpha 2 times 0, that's 0, plus beta 2 times A. So it is beta 2 times A, and this is equal to 2 pi, because I have I and J is the same. So this is 2 pi, implies beta 2 is equal to 2 pi over A. Okay, so I got all the components, sorry, this is here vector B1, this is here vector B. So I got all the components of B1 and B2. So let me write it over here. So now I have vector B1 as a vector. The components are pi over A 0, right? And B2 as a vector 0 and 2 pi over A. Now, let's write vector G. Let's write vector G. Vector G is equal to V1 vector B1 plus V2 vector B2 implies vector G is equal to V1 times vector B1. What do I have here? I have pi over A in the direction of X. So it is V1 times pi over A in the direction of X plus, there is nothing in the direction of Y, plus V2, B2, I only have a term in the direction of Y. So V2 times 2 pi over A in the direction of Y. I have nothing here in the direction of X. So this is what I get, I just have to put my vectors. So this is vector B1, vector B2, vector G, vector B1, vector B2. This is vector G. This is vector X, and this is vector Y. So what I get now is exactly what it's asking me to show, because this is here vector G is pi over A V1X plus 2 pi over A V2Y. So I proved what the question is asking me to prove. Okay, and by this, I reached the end of today's lecture. It's mostly math, I know, so I hope by now you know if you have direct lattice vectors, how you can change them into reciprocal lattice vectors. I highly encourage you to do them for the FCC, lattice described here. So start by A1, A2, and A3, do all the derivations, okay? And you will get what are the lattice vectors for the FCC. So that's it for today, and I wish you best of luck.